Fantastic. Oh.
Yes, I'm Niklas Lundström. And the first degree was a Master of Science in Physics. In engineering physics.
Is that Teknisk Fysik?
Yeah.
Okay.
Teknisk Fysik. From Luleå University of Technology. Luleå. This was in 2004. And after that, or let's say first that I did my thesis in mathematics in dynamical systems. Thesis, dynamical systems. I had a very good teacher there, inspiring. And that resulted in that I did a half PhD. Unfortunately, that supervisor, he had no money to hire PhD students. But in machine dynamics, there was a lot of money, but not that much mathematics. Still interesting problems. We ended up there, and it is a rotor dynamics. 2006. But this was also the same place in Luleå. Luleå. After 2 years there, I missed the theoretical mathematics. I felt that, okay, I think I need some more theoretical research education, a little bit broader than this, because most doctors with this background, they go out in industry and work. And I wanted to have the opportunity to do research in some field I didn't really know what field, but mathematics or some application to another direction. I started to apply for more positions, but still I wanted to stay in the north of Sweden, so I applied in Luleå, Sundsvall, and Umeå, and I got this position in Umeå, which resulted in a PhD in analysis of PDE. PDE in Umeå, or at Umeå, 2011. And this work was about P Laplace equation, or P harmonic functions near the boundary. Boundary behavior of P harmonic functions. You know, harmonic functions. Laplace equation. P harmonic. Then you get a nonlinear version. Like this. This is nonlinear problems.
Who?
Yep. What?
Who was your supervisor in Umeå? Your advisor?
Yeah, my advisor here was Chinese. Very good mathematician, in my opinion. He moved to Uppsala. And he's there now, right now, professor there. What happens next? After this, I had a year still with PhD supervisor with Kai, at a stipendium, postdoc. Let's say postdoc 1 in Uppsala. And then another postdoc here in Umeå. And here we did still PD, but a little bit in another direction. Optimization related. PD theory. Still very theoretical. And here, I continued with the above. I think I should say that. So the above problems. Plus some population dynamics. And some sampling problems. And what more? Stability problems of dynamical systems, perhaps included in here. Okay, this was, now the year goes up to 2012, 2013 should be 13, and then 15. And then I have a tenure track. Here in Umeå, 2020. And now I'm lecturing here. So then you have all the history of my employment in academia. Master of Science, half PhD in mechanics, mathematics, then 2 postdocs with PDE problems and population dynamics, PDE problems, some sampling problems. Also, I have done some management. We continue here. What problems did I do here? At the above, plus management problems. Management of hydropower plants. Pest population.
Is that? Sorry, I was just wondering, is that something that grew out of the population dynamics and the differential equations?
Exactly. I should perhaps do some coloring here. Let's say that I've tried to summarize the main fields. It's me. Can you see? Main field. Or fields. I should say that it's applied to dynamical systems. And analysis of PV. These two. And then, as you say, these goes there, and also I should say that the thesis here, even though more theoretical, but what I learned here was applied here then, in the rotor dynamics half PhD. And then when I switched there to more mathematical direction, I say this is the analysis of PD, and this is green, which follows here optimization and PDE. And This one is related to also here, because we apply theory from there in here. Then. So we can say that both fields goes through from applied to non-applied and vice versa. So, and also they have some paper, I've done some papers in sampling, but perhaps I've done it in 1 year or so, so we can skip that. But anyway, the focus is, for my research, it's not very focused, it's more spread. Now we come back to why. If you don't have any questions here. Then I will talk a little bit about why I have done this.
Oh, so I think we have some questions.
Yeah.
In which discipline your bachelor was?
My bachelor is my first exam. Yeah. It's engineering physics.
Engineering physics. Okay, the master's. Oh,
In engineering physics. I had,
okay.
when I started here, I didn't have a plan to be a mathematician. It was more I want to be an engineer, and I didn't really know what kind of engineer. So I chose the toughest, most theoretical direction. And then the same happens in some sense when I wanted to take a PhD. Then I started with applied, but then I chose something that is very theoretical to be able to choose later on special research.
Like in Sweden, I saw in many universities they have this degree like this one, the engineering physics. But actually, what it is like, I mean, I don't know because I didn't do my bachelor here. What is the main difference of it from the theoretical physics? Like in my bachelor, I studied mathematical physics, like the courses thermodynamics, statistics, dynamics, cosmology, astronomy. This. So what are the main differences from that this degree hold, like this engineering physics?
I think they are quite much the same, I should say, because it's engineering physics. It was not very applied.
Okay.
So quite close to, I guess, quite close to what you have. What you mentioned. A lot of theoretical courses in quantum physics and material science, and also a lot of math courses.
Oh. Okay. Yeah.
More questions?
Thank you.
I had a question about how you got into hydropower plant management. So it sounds very cool. You managed to find a way of applying your research on partial differential equations. But how did you get into contact with the people at the hydropower plants? Or how did this happen?
Yeah, it started here because the problems I worked with up here, rotor dynamics, was actually generator vibrations in hydropower plants. Generator vibration problems. In hydropower. So I was in that field already, and I say also that I have continued working with those persons and those problems a bit during the time. So, and then
that's a really nice thing, because it's often so hard for people who have the theoretical knowledge to actually work that can be useful in applications, to have the contacts and I guess the know-how to be able to make this sort of transition, this bridge between the theoretical and the applied.
Yes, yeah, it's still very difficult to, really get something that they can use. We are trying to do that. We're not really there yet.
And would you have? And I was wondering, would you have any general advice to someone thinking of trying to bridge? I guess perhaps your own background is a lesson of sorts, in the sense that you make sure you learn a lot of applied things as well as theoretical things. So you think that's what allows you to make this bridge between pure mathematics and applications?
Yeah, my dream is to work in both fields, and then I'm not really succeeded. I've succeeded in doing applied math and pure math, but the connection to the industry is not really tight. I mean, I talk to some people there and I ask for problems, but in the end, the problem I will solve is set up thing, and I can show that, you know, that I'm not really there yet. But my strategy is to do both of it, and try to convince people in the industry that I want to help you. I think that this will be useful. Yes. But when I started research, I thought that it would be more like when you are a mathematician, then you get problems from industry. You get problems from physicists and biologists automatically. That on my desk there should be a bunch of problems and I can help them with. But it's not really that way it works at university here. So I have to search for problems. That's my experience of it. You have to go there yourself and show that I can do something. And then perhaps they say, okay, but you're a mathematician, then what can you do? It's a little bit like that. So
the problem, I guess, is you have to. They have problems that they need you to solve for them, but they don't know that, and you have to convince them.
in some sense, perhaps it's in that way. But then it's quite cool that this optimization theory, the optimization PDE theory, is very suitable for production planning. When you have different, you can run something in different modes and start and stop. I guess you have studied optimal stopping problem, and this is more an optimal switching problem. Then you can run in mode 1, 2, 3, 4, 5 and get different outputs. Then you get a system of PDEs. You can rewrite such a problem to a system of PDEs and then solve it numerically to get the strategies. And in hydropower plants, you have like a switching cost. Every start and stop is tears on the machine, and then you get problems like studied up here. Then you can estimate the risk for breakdown or cost of switch and plug it in here and then get the optimal strategy. If you think this sounds interesting, then in the autumn, hopefully we'll have a seminar on exactly this in our research group. More questions? If not, then I think I should say something about why this has happened. And why don't I have such a great focus on the research? Why is it more broad? Why not focused? But broad. Yes, because I had to think a lot of this because I didn't really know directly why this has happened. But one should be that I like to solve problems. And second, I do not like to read. And third, it must be fun. These three things, I think those are properties of myself. They have forced me to to switch subject. Because if you take these two together, then you get no expert when it comes to research. If you do not are motivated to read and read and read what comes up all the time, then you get no expert. But if you go for these, or this one, perhaps this. Oh, it should be one more here. 4. I like variation. Then those reds, they applied it. I switched problem. So what I'm trying to say here is that you have to listen to what you really like to do. And you come up to a level of PhD. Before that, you just have to, you have to work hard and do what you have to do. But when you get possibility to choose, then you try to choose. You try to think of what do I like the best, and then you focus on that. Then you get motivated and you continue. You can continue.
So when you say like no experts, so basically what you've avoided to do is pigeonholing yourself. You basically know a little bit of everything rather than a lot about a very narrow area. Is
yeah.
That yeah.
This is what had happened, and then it's a good in one way and not in another, but it works and it keeps me motivated. So, I have done one paper and I usually switch to another, and then I switch back and go like this.
I think I have quite a similar way of functioning, so I can relate, and maybe I can say that it's what's great is that now that you basically have a research position that's fixed, it's actually a lot more sustainable. It'll be easy to still be excited about your research in 10, 20 years because there's so much variation. But the hard part is maybe the early part of the career, when you're a generalist and you know a jack of all trades. So I think my experience from talking to others, and I don't know, maybe you could say a few words about this, but as if you're not a specialist, it's harder at the beginning of your career, but there's a payoff later on, because then you have broader interests, etc. Would that resonate with your experience?
Yeah, the hardest thing was when I should start to write an application at that stage, because then the question comes, in what area? Okay, and I asked, okay, let's take this area, but I only have done this, and then this area, I only have this, and then this. So I had to find an area where I can strengthen myself through most as possible of my papers. But they are so spread, so I had to, it was not easy, I must say. So,
yeah.
So, people ask you, what are you doing? No, I have to think about what I'm doing before I answer them. And then what application should I write? And it was when I got this money I got from Vetenskapsrådet then, it was about PDE theory. But then I could relate it to management of hydropower then. And also that makes the bridge to what I did in machine dynamics. So I could use also that in. So I got it together quite well. I think I should say something before I say a bit about PDE theory. I should say something about how did I get this work and how did I succeed, or what I think is important when you are trying to become a researcher. My view is that. How did I succeed or succeed? What is important I think it depends on who you are, of course. But there are some points there. The first one is keep your interest out. And how do you do that? I did it by listening to these 4 things. What do I like to do? Listen to yourself. And then, of course, this must be here. Hard work, of course. And then the first thing, make it work with the rest of your life, if any. If you have a life besides, you have to make this research a part of that or make it work together with that. It's very important, I think. And how did I do that? This one doesn't need an explanation, I think. Hard work is hard work, but how do you do this? It depends a lot on who you are and what is the rest of your life then. But again, what do I like to do? And yeah, stay at home, be with my family, and do other hobbies. That's my life very summarized very quickly. So for me, work from home, yeah. Then each break I take can be optimized. Any break can be used to do something that I also like to do, or be with my family. I just go out and do that, get energy from that, and put the energy back into research. Optimizing every break from research. For me, research is a hobby. It's not only a work, it's a hobby. So, yeah. Comments on this?
I guess one of the tough things is once one has a family, that there are family pressures and work pressures, and juggling with the two of them. So how does one deal? How do you do to find a balance? Because now you're a lecturer, so you have teaching duties. I guess you have missing children that you're distant lecturer, so I think you have some of those as well. How do you juggle it all?
No, 3 children. And then if I take a break, then I can go out and bicycling with them. And if I'm at home, I can go lunch with them, and I get more time with them. And also when the time when I do research is not fixed. If I go work at 8 to 5, then I have to work then if I'm tired then. What do I then do? Okay, then I have to do some teaching duties. But if I don't have any, it's not very nice, because then the time is some way spent. But if I'm at home, then I just go out and do something in the garden or children with them, and do them when I'm tired, and then I can go back and do research later on. But
it's interesting.
Very flexible.
This reminds me, what you're saying reminds me of something that Terence Tao wrote about actually being flexible about planning. So he says actually at certain times one is tired, is not motivated. Actually, one should go and do something other than one had planned. Like one should not do research if one is tired. It's counterproductive, because you just make you hate the research and you won't move forward. So this is something you apply yourself. So you're kind of flexible if you're in a mood to work, then you go full in. If you're in a mood to do something else, you do that, and then you come back to work to research later.
Exactly, because also it's this that when the brain is tired, your body is perhaps not tired, or if your body is tired and your brain is tired, and you go out bicycling with your children, then your pulse goes up, and that is perhaps the thing that you need. Some little exercise, or you are tired and bored and not feel well, but then if you are with your family, you can be more happy. You perhaps you will not be a bad parent because you're tired of mathematics. You mean you can be then, get energy, you give energy there, and then you have to be flexible and transfer energy between activities. That is perhaps what I'm doing. And also the brain. I think the brain, my brain works with a problem that in the background, because sometimes when I sit and do something else, something practical, then I get it. Okay, now I understand why I didn't find it out this morning. And then I can go away, write this down, and then go back. So
I also recognize that.
Yeah, I also. I'm not a 8 to 5 worker. So, but that depends. That is because of my. I'm like that. Perhaps it does not work at all for others. I know colleagues that they have to have this border between work and life. It works for them. So you have to listen to yourself. I think. Do I have some time to say something about what is analysis of PDE and what do I do, or do you think we have time for that?
Sure. Let's hear a little bit about analysis of PDEs.
Analysis of PDE, or how do I work? To give the picture of it. Let's take a very basic, important result for solutions to PDEs. We consider the maximum principle. For solutions to PDE. So let's make a sketch in 3D. And we consider a domain in the plane. Let's say it's omega with a boundary. And then we have some solution. We solve the PDE over this domain. So I get a function u, okay? Solving, for example, a PDE of the form in its most general form, it usually written like this. Or here it should be xy then. But then the function, the gradient, the Hessian in some weak sense. And in many problems you are interested in, that's very natural, you're interested in where is the maximum of your solution. And the maximum principle, it states that the maximum is attained on the boundary. Maximum principle states that maximum of u over omega. It's equal to the maximum of u over the boundary. So the solution attains the maximum on the boundary. I guess this problem is so basic that you don't wonder, why do I want to solve this? Why do I want to check if this is true? It's very interesting to find out where is the maximum for some solution to some equation. And how do we then do this? So, how to find out? If, let's call this star, the maximum principle. How do I start? If I want to know if this is true for a very general equation, I should say that first, we try to think of something where we have intuition. So we take some situation that is simple, not too simple, but simple, so we have some kind of intuition. Think of a special case where you have some intuition. Try to break down the problem in a small, simple one, and take some thinking there and use what you know. See if it holds. For example, here then, in this case, you have studied physics, perhaps I've done that, so, or you have just been outside and you know how temperature works. So we can take Laplace equation. This models stationary heat flow. Stationary, or at equilibrium, heat flow. So if you think of the Laplace equation instead of a general PD, then we can realize that, okay, there can't be any maximum in here that is not on the boundary. Because if it's very hot here, in case of the heat equation, assume it's very hot here. And this is stationary heat flow with no source. It can't be an equilibrium, because if we have this heat distribution and the boundaries are fixed, and we let it go, then this will flatten out. Poof, it goes down like this after sufficient time, and then you have equilibrium, which is modeled by this. So then, by intuition of heat, we realize that, okay, it must hold. For this case. Okay, then second step. When you realize what is true, then you have to prove it. Or this will be proved already. So, or find the proof. Okay, you find the proof. Okay, then we have the proof for the heat equation. We know that. Not new, not very exciting, but you know something. And then 3. You want to do something general, okay? You hope to find something new. Then we try to push the limits for this proof. We go backwards, up, and see. what are the assumptions we need on the equation in order to still find this ID to work. So go back through the proof. And find what is necessary assumptions or you try to generalize this proof ID. Generalize proof ID into. Then you will find out something that, oh, at least it holds for this and this and this equation as well. That's the Laplacian. What do we do next then? Probably when you've done that, you will find out where it stops, exactly where this proof stops. There are several steps in it, but you find out this assumption is needed because of that step. So then you improve the proof. Try to find a new ID to replace the ID that stops exactly the generalization you want to do. So you find the critical point here where it stops, so you create a new proof. So improve the proof. And then repeat again. Repeat this procedure. You repeat the procedure until you see that, okay, it has converged. You don't get any better result. Then you write a paper. Okay, even if it's not publishable, yeah, everything is publishable nowadays, but even if it's not a very good one, you can write it down just to have it there. Perhaps you can find out something in the next year or so. It's always good to write down your thoughts. So, point 5, you can do more. Now we go back to physics or applications and see what other problems than the heat equation satisfies our assumptions. So go back to see if we can find other applications of your results. Go back to applications in AE physics. Perhaps you find a new result for some strange fluid that the maximum principle must hold, and you can do something there. That's the strength of mathematics, because starting with one physical problem, you do applied work and you get something out. Then you go backwards and generalize it. And then you can go down again in some other direction and find results in physics. Perhaps you find something new there. Okay. And at this step, this first step, you might also, you say, if you work with pure mathematical analysis, you can also do some simulations and set up a special case and use computers and see what's happened. An experimental case, or experimental stage. And then mathematical part here, starts here and go there, yeah. Comments?
Let me unmute myself. That really resonates, especially this proof mining, as some people call it, is actually a very useful thing. It's something I've always admired in other mathematicians when they're able to not just be satisfied with the proof, they actually try to read it and reduce it to its purest essence, see actually what is unnecessary detail and what's actually important, and then realize, oh, but this proof does a lot more. It's a very important skill. I wish I was more disciplined about doing exactly that, but that's a very nice introduction to problem solving, Niklas.
Unfortunately, I think that it's the system pushes to publish a bit too fast. So what you're saying here is that this part is, when you go back, one should perhaps do that even more, but you need the time, because when you have a publishable result already, the system says, oh, you should publish, but I think it might be a good idea to even anyway push your thoughts more to get something really good before you write. But in the career, you can't just stay too long on one problem either. I used to say that to the students, that you have to get something out of it also. You have to get something done.
Yeah, I think that's for young young graduate students, probably the priority is getting things out in the early years. I was thinking to actually first, maybe Misha, do you have questions? I see the other two have disappeared. Do you have any questions or comments?
No, not on this section actually. I was thinking, I was just looking into this problem because, to be honest, I just did some applied things. My mathematical analysis knowledge is not that good. That's why I have admitted to this program. So I was trying to understand what it is and digesting it kind of. Yeah, because in our country, this is a problem in the university. Like when we admit in the university, we have a lot of students there. So in the very beginning, they separated the students into the field. Like if you want to study, you will just the analysis, then you have to go to the pure math section, and the whole 4 years of their bachelor they study this. And if you cannot study both, because we don't have that option. It's a small country with a big population and too much student. So teachers, they are also forced to do it. So I didn't study that much analysis actually. That's why I was trying to understand. So I mainly studied only the applied math and the mathematical physics this term. So yeah.
But you have the possibility to do it now here.
Yeah. And here also, like in Sweden, you have chances, like you admitted to one program, you are not liking it, then okay, next semester maybe you can apply again and change it. But in Bangladesh, we don't have, because each year there are millions of students who completed their high school, and we have to face for admission test. Maybe I admitted in applied math and mathematical physics. So in the admission test, we are almost 40,000 students, and there was the seat in the university for only 100 students. So if I don't like it and I wanted to study some mathematical analysis, but it was not possible for me, and for that I have to wait 1 year, then sit for the admission test again. If I get qualified with this high competition, then I can study, otherwise not. So that's why I couldn't study so much analysis actually.
The idea of 40,000 students competing for 100 places makes our kind of the queues for our master's programs look look a bit
if you see in the YouTube, you will see a lot of video there. I mean, how they set the question. It's like 100 question, and we got 60 minutes. So it's 36 seconds for each question to solve, like the high school math and physics, chemistry problem if you want to get qualified, and also English and some this kinds of stuff. General knowledge. It's actually very different from here. So we didn't have that much freedom to study what we want actually. Sometimes, like, because I was at the time, I was not a grown person. I just completed my high school. I didn't understand what I want to do actually. Okay, then okay, I want to study this one. But at the time when I studied 1 year, then I thought that no, this is just something I am studying like in the thermodynamics. You of course know about that, Niklas, like Bose-Einstein statistics. So it's they have already proved it. What I have to do is I just maybe some math problem according to their proof, or in the question they write it, okay, prove the Bose-Einstein statistics, how they proved it. So I just memorized I remember some mathematical terms, and I had to prove in the exam. The question is like that. So after 1 year, I didn't actually like that too much. This is what I'm not learning actually, or too much, not too much activity. Here in Sweden, I did some mathematical course in Stockholm University and KTH, not the program course, but here they separate the whole course like 3.5% of the credits from the assignment and 3.5% from the exam or oral exam. And in the assignment, teacher here in Sweden, they set the question where a student has scope. They get time 10 days for an assignment and time to think and make their own assignment. It is not that if you can just Google it, you will get answer. But in Bangladesh, we just had 100, mainly the full course on the exam, and you have to do well in the exam. I just got one exam here in like Sweden. I did a course last semester, number theory in KTH, and there was no assignment, nothing, no oral, just the full, everything depends on the exam. So that's why. And after studied 1 year, I didn't like my bachelor program too much. I wanted to change, but actually I was not brave enough to again sit for the admission test or something like that. Yeah.
Yeah, it's just reacting to something you said. It is a pity not to be able to dabble in several subjects, because something which emerges quite clearly from Niklas's talk, I think, is it's nice to have to be able to study both some applied things and pure things on the side.
Yeah.
So I think the best people, applied mathematics, the best people in applications are the ones who have actually worked on both sides. So I think if you're in an applied field and you've got a strong mathematics background, there's going to be a huge help to you.
Yeah.
And correspondingly, if you're a pure mathematician, but you've got a good grasp of what's actually important in applications, your research will be a lot more interesting, and you'll have a great source of problems. So
yeah.
I think Niklas is a model to us in terms of straddling the two worlds.
Yeah.
Yeah, you use things from different fields and get it together, and you learn in one field and you use it in another field.
Yeah.
Also.
Yeah. Anyway, I think it's. I see that Eric has logged on. So hi, Eric.